Hi everyone, my name is Selena and today we'll be talking about the Friedel-Crafts acylation of ferrocene. This is my poster and I will be explaining in depth each part. So the acylation of 1.528 grams of ferrocene was conducted using acetic anhydride and phosphoric acid. Only a 29.78% recovery was yielded because of poor experimental techniques, but the melting point of the substance was calculated at 81 to 82 degrees, which is really close to the literature melting point, and therefore we can conclude that there was purity in the substance. A TLC plate developed in 30:1 toluene ethanol was used to separate the components of the recovered products based upon polarity. The RF values of pure ferrocene were 0.98. The crude product had ferrocene at 0.98, diacetylferrocene at 0.45, and acetylferrocene 0.42. The purified product of diacetylferrocene was 0.49 and acetylferrocene was 0.45. So carbon-carbon bonding is essential for the synthesis of complex molecules, which are abundant in organic chemistry. One of these processes, Friedel-Crafts acylation, is essential for the electrophilic aromatic substitution of an acetyl group to a desired aromatic molecule. In this case, the acylium ion is needed for the reaction will be generated by acetic anhydride and phosphoric acid. The ion will be applied to ferrocene. This molecule contains two cyclopentadiene rings, which makes it possible for multiple substitutions within the EAS reactions to occur. Recrystallization by hot filtration using decolorizing carbon, TLC analysis, and melting point determination will all be conducted. So here we just have the mechanism of the acylation of ferrocene. So as you can see, ferrocene's reaction is treated with acetic anhydride and phosphoric acid to create the acylium ion that's needed. And because the acylium ion is being applied to the cyclopentadiene rings of ferrocene, multiple substitutions can occur as you see in the products. There is either a monosubstitution or a disubstituted product. So based upon this balanced equation, we can tell that ferrocene is the limiting reagent, and because we're using 8.1 millimoles of ferrocene, we should end up with 8.1 millimoles of acetylferrocene because they're in a 1-to-1 ratio. This makes the theoretical yield of acetylferrocene 1.8 grams. So now I'll go over the methods of the reaction. So 1.5 grams of ferrocene was heated in a boiling water bath with a magnetic bar, and this is figure 3 shows the original appearance of the ferrocene. In a fume hood, 5.0 milliliters of acetic anhydride and 1 milliliter of 85% phosphoric acid was added and heated until the ferrocene dissolved. A reflux conductor with a calcium chloride drying tube was then added to the reaction mixture and heated in the water bath for 10 minutes. So after the addition of acetic anhydride and phosphoric acid, the color of the reaction mixture turned to be a rusty orange color. So now I'll go over the methods of the workup and purification. So first, the reaction mixture was poured onto 25 grams of ice and rinsed with 2 5 milliliter portions of ice water and stirred with a glass rod. Next, the 37.5 milliliters of 3 molar aqueous sodium hydroxide was added, following a little sodium bicarbonate until the mixture was neutralized and stirred. It was tested with pH paper to make sure that it was no longer acidic. So this is the reaction mixture after the addition of sodium hydroxide. After 20 minutes of standing, the crude product that you can see here was collected by vacuum filtration, and a little bit of the brown crystals were saved for TLC analysis, which was before purification. So to purify the sample, the crude solid was boiled with a stirred bar and 20 milliliters of hexane for 5 minutes. A spatula full of decolorizing carbon was added to the hot mixture and then removed by hot filtration. The flask was cooled to room temperature and placed in an ice water bath, prompting recrystallization, and the product was collected by vacuum filtration. So these are the final crystals that were collected. So the methods that were used for the characterization of the substance were melting point, and this is the apparatus that was used, and TLC analysis, and this is the TLC plate, which was used to separate pure ferrocene crude product and recrystallize acetylferrocene in 30:1 toluene ethanol solution. So just in case you needed further reference, this is a separation scheme of the Friedel-Crafts acylation of ferrocene, which we explained before. So for the equipment setup, this is where the reaction of the acylation of ferrocene took place with this, using this apparatus. And the vacuum filtration apparatus, which was used to collect the crude crystals and the recrystallized product. So these are the results tables that we'll talk about in the next 2 slides. So first, we can discuss table 1, the percent yield and melting point of acylation of ferrocene product. So following crude recrystallization, the purified product was collected by vacuum filtration. 0.548 grams of acetylferrocene was recovered, yielding 29.78% of the original sample. This low recovery is a result of flawed experimental execution, which could have been possible in the process of crystallization. For failure to place the reaction mixture in an ice bath after it cooled prevented optimal crystal formation. The melting point analysis of the product was conducted and found to have a range of 81 to 82 degrees Celsius. The literature melting point of acetylferrocene is 82 to 83 degrees Celsius or 84 to 85 degrees Celsius, which aligns with these results and proves that this recovered product was pure. So now we can talk about the table 2, the retention factors of analytes and 30-to-1 toluene ethanol, which is what the TLC plate was developed in. The ferrocene had a retention factor of 0.98 because of its very nonpolar nature, and the crude product shared this retention factor, showing that it still had traces of ferrocene, as well as factors of 0.42 and 0.45, which suggest that 2 other more polar molecules were present. The mono-substituted recrystallized product, named acetylferrocene, had a retention factor of 0.45, and the di-substituted recrystallized product, diacetylferrocene, had a retention factor of 0.49. In the crude and recrystallized product, the di-substituted molecule traveled further than the mono-substituted molecule. And this is because the extra acetyl substituent on the diacetylferrocene has makes symmetry in the molecule, which allows it to travel farther than the acetylferrocene product, which only has 1 acetyl group. So to sum up, we only had a 29.78% of recovery of the pure acetylferrocene because of poor recrystallization techniques, which was 0.548 grams. The melting point of the substance was 81 to 82 degrees Celsius, which shows that the purification was successful of the crude product, and the TLC plate showed retention factors of several molecules, and to show that the purified product contained polar acetylferrocene and diacetylferrocene, and the diacetylferrocene traveled further because of the symmetry within the molecule, and the elimination of the factor 0.98 supports complete reaction of acetic anhydride with the original ferrocene sample.